The differentiation of f of x is equal to ln of x. We know if y is equal to f of x, then dy by dx is equal to f dash of x is the limit as h goes to 0 of f of x plus h minus f of x over h. So for our function, f of x is equal to ln of x. F dash of x will be the limit as ln of x plus h minus ln of x over h. Now, from the rules of logarithms, we have the log a of x over y is log a of x minus log a of y. So we're going to now apply that in reverse. So we now get f dash of x is the limit as h goes to 0 of the ln of x over h divided by x, applying this rule, over h. Now this becomes ln of 1 plus h over x over h, as h goes to 0, and it will become ln of a limit of 1 over h ln of 1 plus h over x. Now there's a rule of logarithms that says r log a of x is equal to log a of x to the r. So just repeat that. R log a of x is equal to log a of x to the r. So what we can do, we can take that power there and put it up here. So we've got the limit as h goes to 0 of ln of 1 plus h over x to the 1 over h. Now, we're going to do a little trick here. We're going to let h over x be 1 over t. So this bit here will be 1 over t. If we do that, what will become 1 over h? Stop the video now and try to think what 1 over h will be. So 1 over h will be equal to t over x. Now, as h goes to 0, this will become 0. So this will have to be 1 divided by a very, very, very large number. So t will approach infinity. So just repeat that. As h goes to 0, this 0 divided by x is 0, and therefore this would have to be 1 divided by a very, very large number. So t will be approaching infinity. So the limit now becomes the limit as t goes to infinity of ln of 1 plus 1 over t over x to the power of t over x. Now this 1 over x now can come out in front of ln. So it becomes the limit as t goes to infinity of 1 over x ln of 1 plus 1 over t to the power of t. So the rule we used here bringing the 1 over x down was this one here that we've already used once up here. Right, now because 1 over x is no longer part of the limit, we can now take it out. So we get 1 over x, the limit as t goes to infinity, ln of 1 plus 1 over t to the t. Now this is very, very difficult to work out, but we could use our calculator to work out some values and see what happens as t becomes very large. So what you should do is make a little table like that and go up in 100 and then keep adding zeros, so 1,000, 10,000, 100,000, and keep going up to 10,000 and work this out to 5 decimal places and stop when you get agreement. Okay, pause the video now while you do that. Right, assuming that you've now done it, this becomes 1.01 to the 100, which is 2.70481. When you do it for 1,000, it becomes 1.001 to 1,000, which is equal to 2.71692. When you do 10,000, it becomes 1.0001 to 10,000, and it becomes 2.71815. When you do 100,000, it becomes 1.0001 to the 100,000, which is equal to 2.71827. Now you might start to remember what number this is. 1 million becomes this, and then 10 million, it becomes this. We now have agreement to 5 decimal places, and we can see that this number here is approaching one that we've already come across already, the number e. So we can say the limit as t goes to infinity of 1 plus 1 over t to the power of t is equal to e. If that's true, going back to our problem, f dash of x is the limit of t going to infinity of ln of 1 plus 1 over t to the t. That would be 1 over x ln of e. Now, ln of e is equal to 1. It's like log to the base a of a. So we've got 1 over x to the ln of e, and we know that log to the base a of a is equal to 1, therefore this bit here will be 1. So we'll be left with 1 over x times 1, and therefore we'll have that the derivative of ln of x will be 1 over x. So the conclusion here is d dx of ln of x is equal to 1 over x. Now if we look at this graphically, using a GeoGebra file, okay, here I have the graph of ln of x. Okay, I have a slider here. Okay, if I move my slider, let's get rid of this. If I move my slider, okay, I can see the tangent and I can see the curve of the derivative being formed here. Okay, and I can see very, very clearly that is part of 1 over x. Okay, so I draw the graph in. See the graph there, and it is f dash of x is equal to 1 over x. Okay, so there's a screenshot of what I've just done. Okay, now there's an alternative proof which you quite often see in books. So it starts like this: let y be equal to ln of x. It's much easier, this proof. Then we know that if y is equal to log a of x, then a to the y will be equal to x. So therefore we can say e to the y is equal to x. If we now differentiate implicitly, so we do e to the y is equal to x, and then we do d dx of e to the y is equal to d dx of x. We know that this bit here will become d dy of e to the y dy by dx, and this, the derivative of x with respect to x, is 1. Now if you differentiate this, you're just going to get itself times dy by dx, which is equal to 1. We want to find dy by dx, so we do dy by dx is 1 over e to the y. Except we know that e to the y is equal to x, and therefore dy by dx is equal to 1 over x. And again we come up with the idea that d dx of ln of x is 1 over x.